All right, so I want to just kind of briefly talk about, I mentioned the concept of like cost and reward of learning something, okay, and dealing with something. Do you guys remember last year, if I were to graph a line, and I wanted to determine, so this is just some generic line, and I'll just put it in y equals mx plus b form for us here real quick. So if I had the line 0.65x plus 9.67, I asked you to graph the inequality of y is less than 0.65x plus 9.67. And I asked you remember shading those things? Okay. And it was maybe not a lot difficult if this was, let's say y is greater than. Okay. If I look at my line right here, what would be greater than? Would it be the blue or would it be the pink? What would be greater than means above, right? Okay, so if I were to do this, make my line kind of that way, kind of drastic, make it horizontal, which would be the above? What color? Be blue, right? Okay, and now as I move it, okay, blue has still got to be the above, right? Does that make sense? Now when I get my line to be like a pretty severe slope like this, people don't necessarily see an above and below anymore. They see a left and a right. Does that make sense? There still is, the blue is still above, it's still greater, but we run into maybe issues on how to determine which one of these we should shade on, okay? So we maybe talked about a rule or a technique that allowed us to maybe do that last year. What if I were to give you something like this, okay? So let me make the line a little bit cleaner looking in terms of an equation. So let's say that that's my line right there, and I'm going to put it in standard form like that. You guys remember seeing an equation like that? Okay, and let's say that I wanted to the only thing with like showing you this is with GeoGebra is that I can't always use the symbols that I want. So let's say that I want this to be, let this one be a less than or equal to sign there, okay? So I want to graph the line that says negative x, or the inequality, negative x is minus 2y is less than or equal to negative 12, okay? You learned last year that you could rewrite that in y equals mx plus b form. You could add x to both sides, divide by 2, and then it would leave you with y is less than or equal to. So you would know instantaneously that you have to shade below the solid line up there, right? Okay? But you also learned another technique, okay? And here's the idea. You could go your entire life of graphing systems of inequalities and use what we just did with y equals mx plus b and be okay, all right? But an alternative to determine where to shade was to just choose a point. Choose a nice point. 0, 0 is a nice point, and I'm going to substitute that. And if I substitute in here, x is 0, y is 0, so it gives me 0 minus 0 is less than negative 12. Would you argue that 0 is less than negative 12? Would you argue that? No. Okay. So this is a false statement. So what it means then is that you were not going to shade where 0, 0 was, and you would actually shade above the line. Does that make sense? Okay. If we were to put it into y equals mx plus b form, we would have negative 2y less than or equal to negative 12 plus x, divide by negative 2, divide by a negative, flips the inequality, so it would give me 6 minus 1/2 x. Does that say greater than or equal to, so shade above as well? Does that kind of make sense? I think, in my opinion, that the substitution of 0, 0 is a much easier approach than changing to y equals mx plus b. And it's safer because when I change into y equals mx plus b, and I may have even stated this at one point when I talked about this at the beginning, is that some people forget the rule of flipping that inequality sign. Does that make sense? Okay. But I'm a person that I would, if you give me the option to stand or sit, what am I probably going to do? Sit, right? If I could sit or lay down, what am I probably going to do? Lay down. If I could walk or run, what am I going to do? Walk. What kind of person am I? Kind of lazy, right? Okay, and that's human nature. Everyone is lazy, but we're lazy to different degrees, okay? But I mathematically, by like writing things by hand, I hate showing work, okay? I hate writing everything out. My hand gets cramped up. I don't like doing it. So if I can avoid, because I know changing a y equals x plus b is a tedious task, if I can avoid that handwritten work, I'm going to. So there's a reward there. I don't have to do so much work by hand. But the cost is I have to know more procedures, right? More relations. I have to know that I can graph maybe this line using x-intercepts and y-intercepts. Maybe I know then to determine where to shade, I have to use substitution of an ordered pair and understand that logic of why maybe I shade where that point came from or I shade opposite to where that point came from. So a lot of times in mathematics, if we want to be lazy and we want to do things the easiest way, then that usually requires us to be very motivated mentally. Does that make sense? Okay? You're going to have to learn several different things. And the reason I'm getting at this is that this thing here is an easier way to do some things. Okay? But we've already got tools that allow us to come up with the same information. So if you want to use this, use it. If not, you don't need to. Okay? But I think it's something that warrants a little bit of discussion, mainly for the reason of where we're kind of at in the year with all these cancellations and delays and that kind of stuff. And today's kind of a weird day because it's a day in between a cancellation yesterday and now 3 days off, right? So I would think that maybe if we were trying to learn something completely new here, we would probably maybe have to revisit that next Tuesday again. So I think that it warrants a little bit of discussion here, and the relationship here that we come up with in the triangle proportionality theorem says if we have a triangle, we know we've got some parallel lines. We have to have parallel lines. It's the only way this works. And they have to be parallel because it guarantees similar triangles. But what this is saying is that you can compare that distance right there to that distance right there. AD compared to DC. Okay? And that will be identical. That will be identical as that distance compared to that distance. Okay? And I'll even show you some other different things that you can compare that's still going to guarantee the same answer. But I want us to know why. Okay? I can give you this proportion, and you just think about all geometry and all math is this way. I can give you this, and you can mimic this in the next problem, and the next problem, and the next problem after that, and that kind of stuff. And you can maybe eventually memorize this proportion is always going to be true, and how to use it, when to use it. Okay? But that's just like monkey see, monkey do. Okay? That's not really learning math, right? Does that make sense? The math is, why is that true? Why can we do this? Okay? And that's what I hope you guys get out of geometry. Not so much, am I going to memorize all these properties and theorems and postulates and that kind of stuff and apply them and maybe use them every day in my life? Because I don't think that's realistic. My hope that you get out of this is that you're able to ask questions like, why? Why does that work? Why is that, when they tell me a procedure in science or a procedure in algebra 2 or physics or whatever, that you have the desire to know why it works that way. Okay? Because what's interesting in all those courses, by now you pretty much have all the math that you need to be able to answer those questions of why. Okay? So let's talk about the why here. If these lines are parallel, would you guys agree that that angle right there is in both triangles? The angle C is in the top triangle and the overall triangle, right? We all see two triangles here? Okay. Would we agree that that angle right there and that angle right there are also congruent because they're corresponding? Okay. So by angle, and this is what I was saying earlier, we already know this stuff. We learned this in section 7.2 when we talk about angle. We know that if I take that small triangle C, D, and then E, and look at the big one then, where this is C, A, and B, that we should be able to take CD, because these two angles are congruent. These two are congruent. So we talked about in 7.2 that you can compare those two sides, right? Okay. Now I'm going to compare them just because it makes things a little bit easier later on. We can skip a property of reciprocals essentially. I'm going to compare CA to CD. So I'm going to go big one to small one. If you want to go small one to big one, it's fine. But CA over CD. Okay. Doesn't that then compare the same way as these blue segments? Can we say that those blue segments would be BC or CB, how you want to say it, to CE? That makes sense, everybody? And I'm going to, just so we can see, I just kind of did a bad way of naming it. Instead of CD, let's call it DC. It'll just make, when we're done, it'll make this show up a little bit more obvious. CE, I'll make that EC. You don't have to do this, but okay. So now here's my question. That obviously is not what we have here, right? Okay, so I want to know why is what we have here in the theorem true? Okay, and here's my question. Is there another way that you can write CA if you know that point D is right there on CA? Can you say that CA is the exact same thing as CD plus DA? Does that make sense? That's the segment addition postulate, right? Can we say, if I put E right there, okay, so this little triangle right here is this triangle over here. What if C to B, or BC, whatever you want to call it, what if that be CE plus EB? Does that make sense to everyone? Okay. So every time I see CA up here, couldn't I call it that? So that's what I'm going to try to do here. I'm going to write CA as CD plus DA. It'll be over DC. And then whenever I see BC, that right there, I'm going to replace it with that. So CE plus EB. And that'll be over EC. Okay. Now let's just kind of make a side note here. What CD is a distance, DA is a distance, and DC is a distance, right? Let's just throw some numbers out here. Let's say CD was 6. Let's say DA is 10. So then DC, which is DC and CD are the same thing, right? So if I let CD be 6, then DC's got to be 6. It's just a different way of labeling the same segment. So that's 6 plus 10 over 6, right? That'd be 16/6. But could I also write that this way? Could I write that as 6 over 6 plus 10 over 6? Does that make sense? I can separate it that way? That's common denominator stuff. But usually we go from the right-hand side there, 6 over 6 plus 10 over 6, to the 6 plus 10 over 6, and then eventually the 16/6. But we can go both directions with that. And the reason we want to do that here is because I can now break this up. We can break that up to CD over CD, or CD over DC, how do you want to write it, plus DA over DC. And on the right-hand side, we can go CE over EC plus EB over EC, right? Now, here's my question. What is something divided by itself? What's CD divided by CD? No matter what CD's length is. It's 1, right? What's CE divided by EC, or CE, again, divided by itself? What's anything divided by itself? 1. So really, this thing turns into 1 plus dA, and I'm going to write this, I'm going to write it as AD instead, 1 plus AD over DC equals 1 plus, I'm going to write it BE over EC. And this is an equation, right? What do those ones do to each other in an equation? They cancel each other out. And if they cancel each other out, you're left with just AD over DC equals BE over EC. Is that exactly what the theorem says? That kind of makes sense? So here's my argument. Is this new? It shouldn't be, okay? Because if you remember what we've done in the past we talked about these two triangles being similar and being able to come up with the proportionality theorem right here, or the proportional statement right here, okay? By looking at corresponding sides. We also said that there was whenever I take a ratio that is existing in a proportion, if I add the denominator to the numerator, that's something we're allowed to do, right? Because ultimately, when I take the denominator and add it to the numerator, okay, I'm adding a value of 1. So this here is that idea. It's not written explicitly like that, but this is the idea that you're allowed to add the denominator to a numerator, okay, as long as you use it to both sides. And that is adding a value of 1 to both sides of the equation. Well, that means you kept it balanced, so if I got rid of that, I'm left with AD over DC is equal to BE over EC. Those two things are the same, okay? So people always say that and this especially happens like back in section 7 too. If I were to give you like this information right here, back in 7.2, the way we had to do this was that we took the 33 and the 27, and we looked at the other triangle, and this would be x plus 33, and this would be 27 plus 18, right? And back in 7.2, we had to go 33 compares to x plus 33, just like 27 compares to 45. And just to save you, I'll do that multiplication real quick for us. So 33 times 45 is 1485. I'll have 27x, and then 27 times 33 is 891. I should be able to 1485 minus 891. 594 is equal to 27x. So divide both sides by 27 then. And x is 22, correct? And that's something you guys already know how to do that. You did that in 7.2. Okay? But what we just learned is also allowable, because some people in 7.2 were saying, I'm not going to do it that way. I'm going to say 33 compares to x. So that distance there compares to that distance, just like 27 compares to 18. Does that kind of make sense on how I'm comparing those, or linking those? And they cross multiply and they get 27x. Okay? Well, if I take 33 times 18, it gives me 594. Divide by 27, and x will be 22. And then the argument is, I'm doing something different than what you did. I did it a different way, Mr. Fay. But did you? Because think about this. This way, the only reason that this door was open to us was because we did this ultimately with that proof before, right? Does that kind of make sense? Okay. So when you do this, you are really doing that. Okay. It just allows you to make your kind of numerators and denominators a little bit more concise. Okay. Now, are you allowed to flip-flop the means? Am I allowed to take like x and 27 in that last proportion I made and switch their spots? If I take x times 27, it gives me 27x, right? If I take 27 times x, does it still give me 27x? So we talked throughout the whole chapter that those things can be flip-flopped. So some people say, I didn't do it that way, Faye. I did it this way. I went 33 over 27 is equal to x over 18. And if you look at it visually then, that's comparing that to that and that to that. Does that make sense? So it's looking at kind of comparing different parts of your triangles to one another. But if I go through that and cross multiply, I still get 27x equals 594. And I'm still going to get x to be 22. But what I want you to understand is that if you did it that way, it's no different than the other two ways. Does that make sense? Okay, you might have different values, you might have different products eventually, you might have different representations of things, but what allows it to happen is the underlying impact of the angle-angle similarity theorem, or postulate, and the congruency, or not together, the proportional sides or corresponding sides that come from that. Okay, and that's the mathematics. And what's I think important for us to understand as you guys go through science classes and you go through other math classes and you learn what seems to be like new things, they're really not. They all come back to something that you already know, especially after you've taken Algebra 1, okay, and been successful in Algebra 1. A lot of your Algebra 2 comes back to those properties, okay. All right, so I don't write this down. You don't have to write this. I just want you guys to investigate this. I think after an example of this, you'll be able to, or I guess the discussion that we go through, you'll be able to make sense of those proportions down. And that's not even all the proportions that could be created here. But I want you guys to just kind of follow me with this here. If I gave you something like this. So all I've done here, guys, is I've created a bunch of horizontal lines. And they don't have to be horizontal. They could be vertical. They could all have slopes to them. Basically, the way I've set it up is that I can take this red line, and as long as I move that red line, all of the black ones stay parallel to it. Does that kind of make sense? Okay. And then I've got these two transversals. Okay. And these two transversals, they can look like anything. Okay. They can be parallel. Let me show you a situation where they're parallel. It's really not interesting when they're parallel because we already know what to do with these when they're parallel. If I have something like that, so the blue and purple lines are parallel, and all of the black lines are parallel, so if I gave you something like this, that shape right there that I just colored in is a what if both pairs of opposite sides are parallel? Parallelogram. It might be a rhombus, it might be a rectangle, it might be a square, but by like its simplest category, it'd be a parallelogram. And when we have a parallelogram, the proportion that I'm going to show you, I guess the ratio that I'm going to show you in a moment would be 1. It wouldn't be very interesting. Okay, it'd be kind of trivial. So let me go back to this. Okay. So that's usually why in your pictures that you would see this, they're going to probably draw their transversal so that they do intersect. Now, here's what I want you guys to see, and the idea that we already know this. If I take that blue transversal and extend it, take this pink one and extend it, do they intersect at a point? And that was the idea that the blue one and the pink one were non-parallel, right? When I do that, do you get that triangle right there? Do you also get...
Please pardon the interruption. The bowlers should be released at this time, and be meeting at cafeteria door. And also, for those that don't know or remember, Monday we will not have school because of President's Day. Thank you.
So you guys see the blue triangle overall there, up to point N, down to I and M. You've got that darker triangle. You even have, didn't mean to do that. You even have that triangle there, right? Does that make sense? Do all of those have angle N in them? Are all of these lines here, which are producing a third side of those respective triangles, are they all parallel? Does that make sense? So as I ask this thing for maybe these angles in here, are those angles always corresponding? Okay, now they're, so that angle there corresponding. This one here, in that one, they're corresponding, right? Does that make sense? So if those angles are congruent, then where my cursor is now, and that angle there are congruent, right? Okay, I know it may be hard to see with those green colors up there. But what I'm trying to get at here is when we look at this picture and this theorem that follows from it, it's just because we have similar triangles. Okay? The argument that gets made here is that look at all those numbers up there. Right? Just find the distances between those points. And if I look at them all, they are obviously all different, right? The way I've got it set up, those are all different values. But I want to take, let's say I take FH, and I divide it by HI. FH divided by HI, it gives me that number right there, 0.63. FH divided by HI. If I take JL, okay, now just humor me here. If I took FH divided by HI, what do you think I should take JL and divide it by? So I take this one, FH, and divide it by HI. What do you think I take JL and divide it by? LM. So let's see what that gives me. Same number, right? So the quotient of those two things are the same. Let's go I to G. Let's go HI to IG. HI to IG gives me 1.75. HI to IG. Let's go LM to MK. 1.75 again. Does that make sense? Same ratio. Okay? Even though all the individual values are different, the comparison of that segment to this one is the same as that one to that one. Okay? And I can move these lines around as much as I want, and you can see that when the values change, these groupings still, I mean, that number and that number are the same, these two are the same. Okay? What if I take, let's just do something like this. Let's jump across the shape now. Let's go FH compared to JL. So this top segment compared to that segment there. Give me 0.87. Let's go HI compared to LM. 0.87. So IG compared to MK. 0.87. Okay? Even if we go let's go F to G. So that's the entire thing, right? The entire blue one. Let's compare that to J to K. Still 0.87. Okay? So in those relations, the fact that those, even though the numerator and denominator are different, the quotients are the same, exists because essentially in that picture, we have similar triangles if we extend those lines to get that third vertex of our triangle. Okay? So when you get questions that look like maybe something like this, and they ask you, solve for X. There's a lot of different things you can do here. Okay? What we're looking at, let's say I take 21. What can I compare 21 to? X plus 5. Okay? So I could take these two distances and compare them. So if I do that, then what should the other ratio look like? 15 over x plus 3. That's perfectly fine. Does that make sense, everybody? Okay. That's usually like the number one way people do these. Could I also do this, though? Could I say 21 compares to x plus 26? Where do I get that at? 21. Yeah. So what I did is I took that distance there as my numerator, right? And then that green distance as my denominator. So then, looking over here, wouldn't that be 15? That's my numerator. That'd be the red distance, right? What should I put that over? X plus 18. It's not the most obvious, okay, but it still gets you the same answer. Gives me x. Eventually, if you solve these, x is 2. Okay. Another way of doing it. Let's say I go. Now this is messy, but x plus 5. So now it's talking about this little distance. Now compared to the whole thing. So it'd be x plus 5 over x plus 26, right? Equals now this little distance is x plus 3 over x plus 18. It's ugly, and just think about the math that's involved in solving that one. You have a binomial times a binomial twice, right? So you got FOIL twice. You have a bunch of x squareds, right? Now they're going to eventually cancel each other out, so you don't have to factor.
An interruption for an additional announcement. I've been asked to remind everyone that tonight is the last home boys basketball game, so please come out and show your support. The theme has also been changed to Pink Out for Valentine's Day today, and there will be no fifth quarter afterwards. So we hope to see you all at the game tonight in your pink. Have a great long weekend.
Are you allowed to change the means in any of these? If we interchange those, if I cross multiply either way, x plus 5 times 15 or 15 times x plus 5, don't I get 15x plus 75? So I can flip-flop those. So let me flip-flop those. I get 21 over 15 equals x plus 5 over x plus 3. Visually, that's how I compare that one to that one, and then this one to that one. Does that make sense? Okay. Somebody in the last class said, okay, I don't do it that way. I didn't do it. I did it in my head. They said, I only get 2115. And this only worked because there's some things going on here with these numbers that I chose that make this happen easily for you to do it in your head. And they say, well, I see 2115 common factor of 3. So they said, no, this is 7/5. And this is x plus 5 over x plus 3. And they thought, okay, the x's are the same, right? So if this is a proportion, they say, what number does x have to be? What could I put there so that x plus 5 turns into 7, and at the same time, x plus 3 turns into 5? What number does that have to be for x? 2. And they thought that they were playing a game in regards to doing it completely different. But that's exactly what our algebra is doing for us when we do our algebra, right? Okay, now if I gave you 21 and 15, and you couldn't, and those numbers were a little bit different to where you couldn't recognize right away what is that number I add to the numerator and to the denominator so that the 21 and 15 numbers become the same, you would go through that cross product process because that automatically generates those for you. Okay? So my hope is that what you see here is some relationships that we maybe already knew, but just bringing them to the surface and saying they are available to you. When you work with proportions, guys, there are a lot of things that you can do that might be looking different than your neighbor or your instructor or whatever, but you get to the same answer. What I want you to understand, though, is that the underlying principle that all of you use that get the same answer, the underlying principle is the reason for being able to do it different ways. Here, the underlying principle is the similarity statements that get created in section 7.2. Okay? And then ideas of allowing to be able to, find reciprocals of proportions, interchange means of proportions, and that sort of thing. Okay. Like I said, I'll open up that chapter test. It'll be due next Friday. There'll be a review with that as well if you want to gain points from that. We will continue. So Tuesday we'll hit the ground running with chapter 8. Okay. There will be some things that we kind of breeze through with chapter 8, and then there's going to be a couple things that we have to slow down and really dive into in chapter 8. It starts talking about sine, cosine, and tangent, that kind of stuff. Once we get chapter 8 down, we're at the home stretch and getting this course done. Almost there. You know what? I may not have. Let me see. I apologize for that. Seven 3, 7 4. All right. I'll give you through. I'm not really concerned. I'll give you through next week to finish, so I'll put them Friday as well. Yep. 3, 7 4. Oh. Okay. Okay. Hello? I'm sorry, you keep cutting in and out. Yeah. That's fine. I'll come down here in a little bit and get it. All right, thank you. Bye. Use it. All right, have a good week laying on the beach. It'd be nice. It would be nice.
Rachel Clark, you have her freshman.
Mm-hmm. Nope, she don't.
But I got her one time. Her mom is my cousin. I asked her mom. I said, "With Rachel, I feel challenged. She's pretty bright. She's the only class she feels challenged is yours."
That's the problem around here.
And that's what Brian doesn't understand.
No,
He
no,
thinks our rigor is top notch.
no. He has no idea.
That's what I tried to tell him the other day.
Like, it's a bunch of,
Our kids want to ask questions.
yeah.
No, we are a small population. The rest of them just want to say, "I don't know."
Yeah. You come into my class, like, I might record it. You come into my class and